This is a quick tutorial of how to do nonlinear dynamic analysis in SeismoBuild. In order to perform nonlinear dynamic analysis, we must first create our model, define the code requirements and perform the eigenvalue analysis. Therefore, we select the Code Requirements button on the Procedure step list once we have completed our model. The Code Requirements window opens, and on the left part of the window, we can see the available codes while only the code chosen for the project, in our case the Euro code, is active. In the first tab, we can see the limit states defined by the code. Since all limit states are checked, code-based checks will be carried out for all limit states. Next, in the Seismic Action tab, we can define the characteristics and final shape of the acceleration response spectrum that is going to be used in the analysis. Selecting the Nonlinear Dynamic Analysis, the Artificial Record Generation module is displayed. 3 methods are currently available in SeismoBuild for the simulation of artificial ground motions: the synthetic accelerogram generation and adjustment, the artificial accelerogram generation, which is the default option, and the artificial accelerogram generation and adjustment. We may select the number of artificial accelerograms to be generated. We can select to generate up to 20 spectrums compatible artificial accelerograms at once. Here we will select to generate 7 artificial accelerograms. We may modify the target spectrum settings, the minimum and maximum period for matching, and the scaling factor for the defined target spectrum record settings. We also may change the time step and the duration of the accelerograms. If we select the synthetic accelerogram generation and adjustment method, some basic knowledge of the geotectonic environment and the soil conditions relative to the region of interest are required. Here we can specify earthquake regime, near or far field ground motions, the expected earthquake magnitude, the distance from the source, and the soil conditions. We click to generate spectrum-compatible artificial accelerograms. Once the artificial accelerograms have been generated, it is possible to visualize the results in terms of both time series and response spectra. We will now move to the next procedure step, which is the eigenvalue analysis. The analysis window opens and we just click on the Run Analysis button to start running the analysis. A progress bar can give us a rough estimate of the time remaining for the end of the analysis, while we can stop or pause the analysis whenever we want. By the end of the analysis, the informative window that pops up informs us about the possibility to check the correct element connectivity from the eigenvalue analysis results. This is because a member that is not properly connected to the rest of the structure obviously vibrates in an abnormal way. Also, when the analysis is complete, a message in the log informs us about this, and about the number of the eigenvalues that were found. Then we click the Show Results button, in order to access the full detailed analysis results. So, in the First Deformed Shape Viewer tab, we can view the natural periods that correspond with each eigenmode, and also, if we check the corresponding box, we can animate the 3D model for the case of each eigenvalue. Here, for example, is the animation of the 3D model for the first eigenvalue. We can also choose other eigenmodes in order to see the animated eigenshape of the 3D model. Let's now choose the third eigenmode. If we want to stop the 3D model animation, we just need to uncheck the Animate 3D Model box. Let's now go to the Modal Mass tab. Here we can see a detailed report of the modal periods, the modal frequencies and angular frequencies, the modal participation factors, the effective modal masses as individual masses per mode, cumulative masses, and as effective modal mass percentages individually, for each mode, and as cumulative percentages. Then, in the Nodal Masses tab, we can see the tables summarizing the nodal masses, for each node, and for each degree of freedom. Moving on to the Step Output tab, where we can see all the nodal displacements and rotations obtained for each node of our model, for each eigenvalue. Finally, in the last tab of the Eigenvalue Analysis results, we can access the Eigenvalue Analysis log, which is also visible in the window where we run the analysis. Having finished with the Eigenvalue Analysis, we will now move to the next analysis sub-step, which is the Dynamic Analysis. We can see that the analysis menu is similar to the one for the Eigenvalue Analysis, so we click the Run Analysis button to start the Dynamic Analysis procedure. A progress bar indicates the time remaining for the end of the analyses, while the analysis procedure can be paused or stopped while running. We can choose to watch the real-time plotting of the top displacement time diagram of the structure. Note that real-time plotting of the diagram may slow down the analysis procedure. For this reason, we will choose to see only the essential information of the analysis. When the analysis is finished, we can proceed to viewing the analysis results in the SeismoBuild post-processor facility by clicking the Analysis Results button. Notice that the analysis results are also saved in a BRF file in the project folder. In the post-processor facility, the analysis results can be accessed using the various available modules. First, the analysis for which the results are shown can be selected via the drop-down list, located at the top toolbar. For example, we can choose to view the results for analysis number 1 or analysis number 3. It is also possible to view information regarding the code-based checks, visualized on the deformed 3D model, by selecting the code-based checks option. We can choose to view the plastic hinges locations and the elements with damage. We can also choose the limit state, for which damage and plastic hinges are shown. By selecting the successive analysis steps, we can watch the gradual deformation of the 3D model, and the evolution of damage on the various structural members of the model. Next, to the Convergence Problems tab. Here, we can get information about convergence or divergence at each analysis step, while we can see details on the elements or nodes where divergence is observed. Next, we will move to the Action Effects Diagrams tab. Here, we can view the internal forces and moments diagrams for each element in the 3D model. By double-clicking on an element, a window opens where we can see the internal forces and moment diagrams in detail for the specific element. We can choose to see the element in 3D view or 2D view. Moving now to the Global Response Parameters tab. Here, we can view 6 different kinds of global response parameters for the dynamic analysis arranged in separate tabs. Specifically, the structural displacements, the forces and moments at the supports, the velocities and accelerations, the hysteretic curves, the total inertia and damping forces, and the code-based checks. First, in the Structural Displacements tab, we can select to output absolute or relative displacements or rotations in the 3 directions. Here, we will choose the relative displacements along the x-axis. For the relative displacements, we must select the node, which we are interested in, along with the base node. Then we select Refresh in order to visualize the result. Moving now to the next tab, which is the Forces and Moments at Supports. Similarly to the Structural Deformations tab, here we can obtain the support forces and moments, in every direction, for all restrained nodes. Here, we can view the total support force or moment in a specified direction, while we can also view the distinct support force or moment at each node. Then we select Refresh, in order to visualize the result. Moving now to the next tab, which is the Velocities and Accelerations. Here we can view the acceleration or velocity of the nodes. We are able to specify the translational or rotational acceleration or velocity in the 3 directions. We select a node. And then we select Refresh in order to visualize the result. Moving now to the Hysteretic Curves tab. Here, we are able to specify the relative displacement or relative rotation, in the 3 directions of global degree of freedom, against the corresponding total base shear or moment. We select the first node. And then the second node. And we refresh in order to visualize the result. Moving now to the Total Inertia and Damping Forces tab. Here, it is possible to obtain the total values of inertia and viscous damping forces mobilized at every given time step of the dynamic analysis. We select Refresh to view the results. Finally, to the Code-Based Checks tab. Here, we can perform the code-based checks and view the results for each member and for every step of the analysis. First, we select the code-based check and the limit state for the check. Then the analysis step. Using the scroll bar, we can access the code-based checks table contents, which include the checked member, the criterion value, the check condition, the performance ratio, and whether the member has reached its capacity limit. There is also the option to include only the checks where members have reached their capacity limits. For example, here we choose this option, and we select Refresh in order to view the new results. Obviously, during the first analysis steps, no member has reached its capacity limits. While, if we move toward later analysis steps to higher load factors, we can see that the results of code-based checks indicate that certain members have overpassed their capacity limit. In the code-based checks module, it is also possible to see the code-based checks history, which is actually the visualization of code-based check results for each element along the analysis steps. So here first we have to select the desired member, and then the type of check and the limit state. So here, we have chosen to view the performance ratios from the chord rotation capacity checks, for the damage limitations limit state, for the end A of column C1 of floor 1, along the local axis number 2 of the element. Which results we can view in tabular form, or as a graph. At the next step, we will see the Element Action Effects tab. In this tab, we can access the element frame deformations, frame forces and frame hysteretic curves, for the inelastic frame elements employed in the structural model. In the first tab, we can visualize the deformations developed by inelastic frame elements, as computed in their local corotational system of reference. The values refer to the chord rotations at the end nodes of each element, the axial deformation and the torsional rotation. So, after selecting the type of deformation, we then select the member we want. And select Refresh to view the results. Next, we will go to the Frame Forces tab. Here, we can visualize the internal forces, developed by inelastic frame elements, as computed in their local corotational system of reference. Again, we can visualize the results by selecting the desired element, and then selecting Refresh. Finally, to the Hysteretic Curves tab, where we can plot the deformations or rotations, versus the internal forces or moments developed by inelastic frame elements. Like we did in the other tabs, we choose to plot the rotations against moments, in local axis 2 for column C1, of floor 1. Then we select Refresh. We will then go to the Step Output tab. Here, we can access tables, with all the results of the analysis, including nodal displacements and rotations, support and element forces, and moments and element strains and stresses, obtained by SeismoBuild, at any given analysis step. After navigating all the tabs, available in the Post-Processor module, we will move on to the next analysis stage, which is the Code-Based Checks stage. In the Code-Based Checks module, we can access the results from different type of checks, distributed in the various tabs of the module. Also, we can view the results in table format, and visualized on the 3D view model. We can reveal or hide the result tables. In the 3D view mode, we can select to view the check results, in terms of colors on the 3D model members. We can select to view the performance ratio of all the 3D model members, in terms of red and green color, on each member depending on whether it has failed or not. And also the performance ratio value of each member. Now that we have the color of each member along with the value of its performance ratio, we can observe that members that haven't yet failed, thus are characterized by a performance ratio of less than 1, have a color belonging to the green scale. A deep green color indicates a member with a performance ratio far from 1, closer to 0, while a more pale green color indicates that the member's performance ratio is closer to 1, but always less than 1. On the other hand, members that have failed, thus they are characterized by a performance ratio greater than 1, have a color belonging to the red color scale. Again, a deep red color indicates a performance ratio much higher than 1, while a more pale red close to orange color indicates a member that has failed, but with a performance ratio closer to 1. Also, by right-clicking on an element and selecting View All Member Checks in the emerging window, we can access all the member checks results for the selected member in tabular view. There are separate tables available for the chord rotation checks and the shear checks. Each tab of the code-based checks facility, for example here in the shear checks tab, we can select the limit state for which we want to view the results. For example, here, let's select the significant damage limit state and observe the capacity check results, visualized for each member on the 3D model, along with the performance ratio values for each member. Like for the chord rotation checks, here for the shear forces checks, we can see that members that haven't failed are characterized by a green color and a performance ratio below 1. Switching now to the Joint Shear Forces tab, where we can view the results for the joint capacity checks for each limit state. Their results can be presented in tabular view or on the 3D model. Similar things we can see for the joint's horizontal hoops area checks, where, again, we can see that joints that have passed the checks are characterized by a green color, and joints that have not passed the checks are characterized by a red color. Now, in all the Joint Checks Results tabs, we can again right-click on a joint, select the View All Joint Checks option, and open a window containing the check results for the particular joint for all the limit states in tabular form. While, in the same window, we can also navigate between all the available types of joint checks, including the checks for the horizontal hoops area, the shear force checks, and the checks for the vertical reinforcement area. We can also reveal the tabular view of the results. Now, let's also see the checks for the joint's vertical reinforcement area. Finally, we have finished the procedure steps of dynamic inelastic analysis of our model. After all this, we can create the calculations report, which we analyze in corresponding video.